Hi guys, this is Siri, and today I'm very excited, we're actually going to be starting our linear algebra series. So let's just write down linear algebra just so that we know what's going on. Okay, and today is just going to be a gentle introduction to what linear algebra is. But you guys might be wondering, like, what linear algebra actually is, right? Like, is it algebra? Is it something that has to do with like linear things? Like, what is it? Some of you might have heard that it has to do with matrices and vectors, and you would be right. And some of you might have heard about, linear systems of equations, and like how we solve them and things like that, and you would also be right. And I also want to tell you that there's some geometry to it. There's a geometric component to this branch of mathematics, and we will be exploring that as well. But what I'm here to tell you is that all of these things are very like related to one another, and we're going to explore each part in great detail, and we're going to see how they all weave into one another and how they beautifully relate to one another. So that's what we're going to try to do in this series. Okay, so before we tackle this beast, let's start slow, and let's start with some formal definitions that we need to know in order to like set up the groundwork and actually dive into like the nitty-gritties of linear algebra. But these definitions you've probably seen before in another class, like in Algebra 1, Algebra 2, or like pre-calculus or something like that. And yeah, let's just start, right? So the first one is a linear equation, which you've probably seen before. A linear equation. Okay, so what is a linear equation? You've probably seen lines, right? Equations of lines, and we can also use like different variables, right? It doesn't just have to be x and y. It can be many, like it can be x, y, z, a, b, c, d, right? But instead of using all the letters of the alphabet, just in case we run out, let's just use like x1, x2, and x3 to denote the different variables, just like x, y, z, and the other letters would. Okay, we don't have to, but it's just like a convention that we start to use. Okay, so a linear equation. So a1 x1 plus a2 x2 plus a n minus 1, assuming that there are n terms in this equation. So a n minus 1 and x minus 1 plus a n x n. Okay, so these are our n terms. So this is just an expression. If we wanted to make this an equation, we would set it equal to like a constant, and let's just set it equal to b. Okay? So don't let these subscripts confuse you. These subscripts are just telling you, hey, this is the first term, this is the first coefficient, this is the first variable, this is the second coefficient, this is the second variable, and so on. It's just telling you the position, right? And these all can represent different numbers, like 5, 9, and 13, and things like that. Okay? So all linear equations can be arranged like this. All linear equations look like this, or can be rearranged to look like this. Okay? So yeah, all of them can be rearranged like that or arranged like that. Okay, so a system of linear equations, however, is just a collection of these equations. A system of linear equations is just a collection equation is a collection of linear equations. Okay, you've probably seen systems of linear equations before. You've probably seen the methods of substitution and elimination, and how when we have like 2x plus 3y equals like 13, I'm just making up numbers, I don't know whether the solutions would be would even exist or not, but like, and x minus y equals 11 or something like that, and you try to solve for x and y. You know, that's a system of equations. That's a system of two equations. You have two equations. You have two restrictions on what x and y can be, and you try to solve for them. So hopefully you've seen substitution and elimination before, but you know, in this series we'll go through and discover a much easier way of solving these systems of equations. Okay, but this is what a system of equations is. Okay, that's what I wanted to write down here. So these are just our like definitions. Okay. So another one, a solution of our system of linear equations, like I said, is you know, the values that make that equation true, that system of equations true. So a solution of the system are the values of the variables, actually, that make the system true. So for example, when we have our a1, well, I don't want to come up with an example, but a1 x1 plus a2 x2, and you have this equation, right? And pretend that you have a2 x2, I mean, you have like c1 y1 plus, c1 x1 plus c2 x2 with different coefficients. These are coefficients. Like when you're presented an equation, you'll see real numbers for this. You're not going to see a1 and a2. You probably might see x1 and x2, but you're definitely not going to see a1 and a2 because you actually want to put a constant in there, like 4 or 3 or something. And you have another equation with like 2 and 5 and things like that. So, okay, let's just say that 5x1 plus 3x2 equals 13, and I don't know, like 12x1 plus like 5x2 equals like 34 or something, right? So you have a system of two equations, right? You have two equations, and your coefficients, right? You have coefficients, and you also have your variables, right? So the values that you put in for x1 and x2, the same x1, the same x2, those are going to be your, so that's going to be one of your solutions, right? Or your only solution. Okay, so the solution of the system are the values of these variables x1 and x2. So you'll have two values, x1 equals something, x2 equals something. You substitute it back in, and now the system is true. Okay, so that's a solution, and the set of all possible solutions, because we're going to see that it's possible to have multiple solutions, actually an infinite number if you're having more than one. But we'll get into that later. So the set of all possible solutions is called well, the solution set of a linear system. It's called the solution set of the linear system. Okay? I know that might be redundant, but just want to put that out there. Okay? And one last thing, a system of two linear systems, so two collections of equations, right? Because that's what a system is, a collection of equations. So two collections of equations, two systems of equations are considered equivalent if they have the same solution set. So if you solve this system and you get x equals 1 and x equals 3, then, and if you have another system, another collection of equations, and the solution to that system is also x equals 1 and x1 equals 1 and x2 equals 3, if they have the same solutions, the same values that you substitute in for x1 and x2 that make the solution, that makes the system true, then they're considered equivalent. Okay? So 2, doesn't have to be 2, it can be 2 or 3, but if they have the same solution set, then they're considered equivalent. Two systems of linear equations are considered to be equivalent if they have the same solution set. Okay? Okay, so each solution for the first system is a solution of the second, and each solution of the second is a solution of the first. Okay, so that's what I mean. Okay, so now let's go into the next page. Let's add a page. Do I have to X this?